Good morning. So we'll get started here. So today we're going to wrap Chapter 3 up in terms of covering most of the content in Chapter 3. And then next Monday and Wednesday we'll have 2 lectures ahead of Wednesday's night exam. So in those lectures we'll look at some review problems from Chapters 1 through 3. This particular problem here is probably one that I would imagine most of you want me to go through again. Unfortunately, I don't think I have time right now to go through this particular type of combustion analysis problem. I'll walk through the summary in a second of how we can approach a problem like the one we were solving at the end of class last time, and then get into the second half of the problem afterwards. But if you want to see problems like this, there's a bunch of examples of this type and all the other types of problems in those daily quizzes, and there's video solutions if you need a particular solution to any problem. So you can check those out on Carmen. Just go to the main page, there's a link to the daily quiz area, or go into modules and look for those. But in general, the combustion analysis is a way of analyzing a compound that contains CH and generally O or any other third element. And the way the analysis works is all of the carbon in a pure sample is converted to CO2 very carefully, where as much of that carbon, like 99.99% gets converted to CO2, then the mass of CO2 is very precisely determined. And then the same thing for hydrogen being converted into water. So all the hydrogen in the sample makes its way into water, and you very precisely calculate the mass of water, so you can calculate how much hydrogen the sample contained. And then the third element doesn't really matter so much what it is, because we're just going by difference. So we're taking the total mass of the compound, subtracting off the carbon and hydrogen. This is how we get the mass of the third element. The only thing we need to know is what the third element is. We need to know if it's O or N or sulfur or some other element. Often you'll see oxygen just to make it slightly simpler, but theoretically you can throw nitrogen in here. You just have to know what that third element is. And then the final part of the problem is kind of going back to like a percent mass problem, of going back to a problem where we know a ratio of masses of the elements. The formula is the ratio of the moles. It's the simplest ratio of the moles is the empirical formula. So we can get an empirical formula if we take the grams of carbon as a ratio to the grams of hydrogen as a ratio to the third element mass, and just simply convert those to moles, and then from there try to find the simplest whole number ratio. Simplest whole number ratio is usually obtained just by dividing by the smallest, and if you don't have a whole number, we have to find a multiple. We have to double, triple, quadruple, and in most examples, maybe doubling or tripling usually works. It would be pretty obvious, like one of your moles might be equal to 1.5, and you'll know you have to double all of the moles. Now that gets you the empirical formula, the simplest ratio of the moles of the elements in the sample. If you want to know the molecular formula, we have to do a second experiment. Mass spectrometry is a general type experiment, one you don't have to understand too much about, other than it was the one we talked about in Chapter 2 on how we got the abundance data on elemental composition and also their atomic weights. And so this is just an experiment where you put a charge on a substance, bend it through a magnetic field. Depending on the mass to charge ratio of the ion, you can count and determine the molecular weight. And so we determine the molecular weight of this compound's 116. We want to know its molecular formula. So previously, last time we determined it was C3H6O was the empirical formula. What we want to do is figure out, each of these coefficients are multiplied by x, by some multiple, should be a whole number, and we should be able to take the molecular weight and divide it by the empirical formula weight to figure out those number of multiples of that empirical unit in the molecular formula. And so our molecular weight's 116 grams per mole, and we would just add up the grams per mole of 3 carbons, 6 hydrogens, and an oxygen. So 12.01 times 3 for carbon, plus 1.008 times 6 for the 6 hydrogens, plus 16 is 58 grams per mole. I could write the extra digits, but 58 is enough to see that this is going to work out to be a multiple of 2. And so there, in this compound, are going to be 2 times 3, 2 times 6, 2 times O number of those elements within the molecular formula. So we're going to have a molecular formula of C6H12O2. So we're just trying to figure out that multiple of the empirical unit. There's 2 of them, so we have to double the coefficients. So I think once you see C6H12O2 as the molecular formula, you can go back and kind of check and say, yes, C3H6O is consistent as an empirical formula for this compound. And so this is a process for how you are able to know the formula of compounds, is through experiments like these. And this is what the sort of middle section 3.5 in the textbook is getting at. How do you know the formula of compounds? It's through the analysis of empirical formula data, and then if you need a molecular formula, through the determination of a molecular weight from some second experiment. So the remaining part of the chapter, and we've looked at one example of this already, and I think if there's probably anything, I'm sure you guys, if you didn't remember the word stoichiometry from high school, you remember the task of figuring out details of a chemical reaction, of like how much product is made for so much reactant being made. So hopefully this is a memorable topic, even if you don't remember it super clear. But stoichiometry is just detailing or quantifying the aspects of a chemical reaction. So we want to be able to take, for some reaction, say you have A going to 2B, you want to be able to figure out, well, how much A could produce however much B in the process. We might want to take, the mass of A in grams, convert that to moles with its molar mass. We look at the coefficients in the reaction, like the 1's in front of A and the 2 in front of B in this example, to interconvert between moles. So we use our coefficients to interconvert between the moles of A that would react versus the moles of B that would form in the chemical reaction. And we use the molar mass of B to go back to perhaps calculate the mass of B. So this is the way stoichiometry works. We use molar masses, of course, to go between grams and moles of substances, coefficients in the reactions to interconvert moles. Mentioned, we can interconvert molecules as well. So if we want to look at this on a molecular level, we could look at the coefficients for being 1 molecule of A, when it reacts, produces 2 molecules of B. So we can look at the coefficients on the mole. So 1 mole of A reacts, 2 moles of B are produced. Or we could look at it on the molecular level, that for every 1 molecule of A that reacts, 2 molecules of B are produced. This just becomes a picture of, are you looking at 1 distinct A making 2 distinct Bs? Or are you looking at a huge collection of an Avogadro's number producing 2 Avogadro's numbers of B, where you have a huge collection of molecules when you're thinking about what the mole corresponds to. And we'll see that there's 2 different ways. Like we can look at problems and maybe use the molecular picture, or we can use the mole picture depending on the way the data is presented. This first problem here is going to be at the molecular level, because I think it'd be nice if we could look molecule by molecule what goes on in a reaction. We can do this to a small level when we have 5 or 10 molecules or fewer in a reaction. I think we can draw a picture, make a particle diagram, make sense of those type of problems. But then once we get into having grams of substances, obviously we're not going to sketch out every molecule. It's going to take quite a while to write an Avogadro's number of molecules. So, but I think if you can understand 1 molecule of A producing 2 molecules of B versus 1 mole of A producing 2 moles of B, then that's the idea. So if you have 2 moles of A, you get 4 moles of B. If you had 2 molecules of A, you get 4 molecules of B. So the moles and molecules kind of go hand in hand, but the picture just changes of what it is that you're picturing. So anyways, we're given this reaction here, so of hydrogen and nitrogen reacting to produce ammonia. So if we had to balance this reaction out, I think we're going to need at least a 2 to balance the nitrogens, and then that's going to give us 6 hydrogens, so we're going to need 3 H2s to go into balance. So we have 6 hydrogens and then 2 nitrogen atoms on both sides of the reaction. So we have coefficients of 3, 1, and 2 in front of H2, N2, and ammonia in this balanced reaction. So when we're doing a stoichiometry problem, sometimes you'll be given the sort of maybe this thing in words converts into this thing in words, and you have to write out the reaction and balance it. And that's one of the keys, is you have to balance a reaction. If we're going to do a stoichiometry problem, we have to have a balanced reaction. So if you're ever given a problem that has underlines for coefficients, it doesn't directly give you the reaction, and you have to maybe consider what the reaction is from information provided in the problem, make sure to take the time to write out the balanced reaction, because we're going to need these coefficients to be properly balanced in order to solve the problem. Okay, so if we have the question, how many molecules of N2 are required to react with 6 molecules of H2? Well, I think you can see the problem is that for every 3 H2s, 1 N2 is required. So if we have 6 H2s, of course, we're going to need 2 molecules of N2. Now, at the molecular level, sometimes you can just sort of picture this out. You can like literally sketch, imagine making like a little box where you have 6 H2s. You may not know the type of bond that forms between them, whether it's single, double, or triple, but you just imagine some type of bond between those hydrogens. So I have 6 of them here. And then obviously you can picture nitrogen turns out to be triple, but again, you may not know this, and that's not such a big deal because we could just be writing this in as like N2 instead of showing the bonding nature if we just want to picture this out. And then what we're going to do is we're going to sort of lasso out, if you will, one of the ends and then the other end with 3 others. And so we can show 3 H2s reacting with one N2, then of course we're going to need, this one and this one to react with one of the ends here, and then the other 3 for here. So once this reacts, this is going to lead to these being gone, and now we're going to have in their place the NH3s that have formed. So we formed 4 NH3s in this process. So every time we took 3 H2s and an N2, we made 2 NH3s, and so we could sort of be almost like canceling out and changing the nature of the bonding between these substances that are taking place in some sort of reaction vessel as this reaction is taking place. So we have options here. We can make a picture, we can sketch things out, or we can just look at the coefficients, use them. The last thing we might be able to do, if you're looking at this saying, well, how do you really get 2 here some other way? If you don't want to sketch out a picture, if you're not getting, or you want some other way of getting 2 molecules of N2, we can use dimensional analysis is another way we can solve this problem. We could say how many molecules of N2 react with the 6 molecules of H2, and then I can just use the coefficient in the reaction. For every 3 molecules of H2 that are required to react, 1 molecule of N2 must be present to react with them. So I get that 3-to-1 ratio, and of course that gives me the 2 molecules of N2. So just about every problem will have this option of draw a picture, make a diagram, think through just how we kind of thought through, well, 3-to-1, so 6-to-2, or writing out the math and solving it descriptively using dimensional analysis. So if 6 molecules of H2 react, we kind of already pictured this, but if we want to show this with dimensional analysis, so the number of molecules of NH3 that are produced from 6 molecules of N2 reacting, 6 molecules of H2 reacting, it's for every 3 molecules of H2, we're producing 2 molecules of NH3. And so 6 divided by 3 times 2 is, of course, 4. I'm going to write this reaction out again, because I'm going to show one final way. And what we're going to see for different problems, like I said, we can solve problems a variety of ways using a variety of tools. And I think having an understanding of how all these tools work, especially for a really simple example, one where we probably knew 2 molecules and 4 molecules for the N2 and the NH3 here without too much effort. But if we can think of the simple examples on how we can use simple tools, and maybe we can use these simple tools on more complex problems where we might really not be able to at the molecular level picture what's going on. So the last thing I want to show is one of these BCA charts that you may have seen in lab or used already. So a BCA chart is one where we just try to think from the information provided, what's present before the reaction takes place, what are the change that takes place during the reaction, and then what's present after the reaction completes. And so in our BCA chart, we might have like our 6 molecules of N2 that were given in the problem. We didn't know the N2. We were trying to figure that out. And then we had none yet of the product produced. But the thing that we know from the coefficients, as long as we're writing in here either molecules or moles, we have to write in the reacting unit if we're using a BCA chart. So the before and change and after, these have to be in either moles or molecules, not grams. We can't put mass into the chart because the reacting unit isn't the gram. The reacting unit is the molecule or the mole of the substance. So as long as we're putting molecules or moles into this chart, then these coefficients are true that for every 3x that I lose, I'm going to lose x of N2 and gain 2x of ammonia. So that the 3 and the 1 and the 2 in front of x or whatever symbol you want to use for your variable here, that for every 3x of hydrogen that we lose, we have to lose 1x of N2, and we have to gain 2x of ammonia. So these coefficients here are just coming from our reactants being lost, and then our product being gained, and then using the coefficients in front of them in front of x. And so then this here is like, well, if I'm obviously consuming hydrogen, I'm consuming all of the H2 down to nothing. So then you can see here that 6 minus 3x equal to 0. X would be equal to 2 molecules. And so that's how we're losing minus x minus 2 molecules of N2. So this is just one other way you can see that the N2 lost and reacted would be 2 molecules. And then the NH3 gained would be 2x. So 2 times x would be 4 molecules. So we can set a chart up, but the key, I think, for right now, what I want you to see is just knowing that the change is just always going to be the reactants losing by their coefficients and the products gaining by their coefficients. Now, like I said, some problems will be tailored or maybe more easily solved with like a BCA chart, others with math, others with the picture. But I think having the ability to comprehend and use these different tools for a problem is, of course, going to be very useful. So now when we look at the combustion of glucose reaction, I think we've written this reaction before, the 6O2 reacting with 1 mole of glucose gives you 6 CO2s and 6 waters. And there's 6 carbons on both sides. So the reaction's balanced, 12 hydrogens. And these 6 plus these 12 oxygens, so these 12 plus those 6, so 18 oxygen atoms on both sides. So just making sure we have a balanced reaction. And then how much CO2 is produced by 2.5 grams of sucrose reacting according to this reaction? Now this problem here, I think, is one where we could make a chart, but then I have to write a chart out. We could convert this to moles and think about reacting units and picture it, but then I have to do some conversions, write things down. I think this looks like a dimensional analysis problem. So this is one where I'm looking at saying, okay, I'm probably just going to do this with dimensional analysis. But I think if you're, so I'm just going to have the number of grams of CO2 equals and kind of try to solve this in one step. Now, the way this could work with the chart might be, if you wanted to think of the chart, you could think of it, and it might be helpful to think about converting this to the number of moles. Because if we do a BCA chart, we want to start with the moles and not the grams. So if we do want to do a BCA chart, we'd want to start with the moles here, and then this is just going to be minus x, minus 6x, plus 6x, and then plus 6x over here. And so the O2 is assumed to be in excess because we're assuming all of this reacts. So we just have enough oxygen, presumably, for this reaction to take place to produce our CO2. And we would have none of the products yet present because we just have, in the problem it says you have glucose reacting to produce CO2 and water. So we don't yet have any CO2 and water. And so if you can figure out the number of moles here and you want to use the BCA chart, do you see how if you figure out the number of moles, you just figured out x, and you just multiply it by 6x, and then convert CO2 into grams, and then you get its number of grams produced. So if you're looking at the chart, you might pretty easily see how you can come up with x, come up with 6x, and then just go back to the number of grams using its molar mass. Okay, if that makes sense, then I think the dimensional analysis steps will make sense. And even if the chart's a little wishy-washy right now, I think the dimensional analysis can make perfect sense, because in the dimensional analysis way we would solve the problem, as we just start with our 2.5 grams of C6 H12O6. We previously worked out, I think it was 180 point something, 180.2 or 3. I think it was 0.3 grams per mole. So I'm not going to bother double checking that because we used that in a couple examples last time. So that's just the molar mass. It's just from the periodic table. So we're just converting to moles of CO2, and then for every 1 mole of CO2 that reacts, or excuse me, 1 mole of glucose that reacts, we're producing 6 moles of CO2. The only moderate thing that's worth thinking is that you're losing this and then you're gaining this in terms of the way the reaction's going. So we're losing the glucose, producing the product. So for every 1 mole of C6H12O6 that reacts, we produce 6 moles of CO2. And so if we want to go to grams, we just use its molar mass. So the number of grams per mole of CO2 is 12.01 plus 16, so it's 44.01 grams. So 2.5 divided by 180.3 times 6 times 44.01. We're producing about 3.66 grams of CO2. So the combustion of glucose produces a fair amount of CO2 from the combustion of glucose. And so I want to give you guys a minute to think about how much glucose would you need to produce this quantity of CO2. So if you need to produce a certain quantity of CO2, how much glucose would be required to react with an excess of oxygen to produce that quantity? So spend a minute working on this problem here, either with yourself or you can work with your neighbors if you wish. All right, so let's take a look here. So did you guys get about 17 grams? That's what I got. Let me double check here. Yeah, I got 17.1 grams. It actually was 180.2. It actually turns out that doesn't even change the numerical answer. So this actually was 180.2, not 0.3, but it still gives you 3.66 in the previous problem. But then 25 grams of CO2, the way we're going to think about how we're going to produce 25 grams of CO2 is just molar mass of CO2, of course, to its number of moles. The moles of CO2 to moles of glucose, and then from the molar mass of glucose, we get the number of grams of glucose that we need. And so we work out 17.1 grams. So 3 grams produces, or excuse me, 2.5 grams produces 3.66 grams. 17.1 grams of glucose reacting with oxygen would produce 25 grams of CO2. So we can work through the problem forward and backwards this way. Okay, so let's talk about another issue, which is, and I've kind of already used the word excess reactant, that in the previous problem we were assuming we had excess oxygen, meaning we had plenty of oxygen for the reaction to take place and we weren't running out of O2. Now, limiting versus excess reactant problems are one where the reaction might tell us that we're supposed to mix 1 glucose and 6 oxygens, but we can mix together whatever proportion we wish. whenever you run a combustion reaction, you usually have a room full of oxygen. So usually you have plenty of oxygen. If you're imagining some other reaction where we're taking, A plus 2B going to, say, C, I can mix A with 3 Bs, and I'll just have some B left over. I can mix A with 1 B, and I just won't react all of the A in that case. And so I can mix together in a reaction vessel or container, or however I'm carrying the reaction out, I can mix together whatever ratio of A and B or reactants I wish. It's just the reaction will stop at some point, and we'll produce only so much product once one of those reactants is gone. The reactant that's completely reacted is the limiting reactant. So we say it's the one present in the smallest stoichiometric amount. And so the A to 2B example, it's not whether the amount of A or B is in lesser quantity in the reaction that determines if one of those is the limiting reactant. It's the ratio of 1 to 2. So if you have less B than that ratio, then you're going to run out of B first. If you have less A than that, you're going to run out of A first. It's all about the stoichiometric excess. And so the excess reactant is the reactant that remains once the reaction has completed. And at that point, at the point you consume the limiting reactant, you've reached the maximum yield of the reaction. So we'll talk in a couple of slides about the percent yield of a reaction. The yield of a reaction is how much of that maximum yield you actually obtain. And so like a simple example, the particle diagram is shown here where we have 10 H2s and 7 O2s, and we're reacting to produce water. We can write out that reaction. We've used this one before. The H2 plus O2 going to water reaction is balanced with 2 H2Os and 2 H2s. So we have 4 hydrogens on both sides and 2 oxygen atoms on both sides. And so the reaction is dictating that we should have twice as much H2 as O2. And you can look at the mixture of 10 versus 7 H2s and O2s and reason out pretty easily that if you're going to react all 7 O2s, you would need twice as many molecules of H2. You would need 14 molecules of H2. So if we want all 7 to react, we would need 14 molecules of H2, but we only have 10 present. And so likewise, if all of the H2 is going to react, then we're going to need half as many molecules of O2. We're only going to need 5 O2 to react with this one. So 5 O2s are needed to react with the 10 H2 molecules. And then we're going to leave behind those other 2 O2 molecules. And so if I have 7 O2s, I need 5 to react. Then I should have 2 left over. So those 2 molecules of O2 are in excess, meaning I could have just mixed 10 and 5. But like I said, I can mix together whatever I want, and just one of them can be left over. And so the O2 is going to be the one that's left over. Now, we can show, because this is like a particle diagram with a small number of molecules, we can actually start lassoing out. Like we can lasso out the red are the O2s, and then the gray spheres are H2s. And so I can lasso out 2 H2s and an O2 together and know that I'm getting 2 waters that form from those reactants. So these are gone once reacted, and I produce the 2 waters in their place. So same thing here. So I have another 2 H2s and an O2, and I produce another 2 waters in their place. I can do this again. So again, I'm losing these and producing 2 more water molecules. And let's do it one more time. Or actually, I can do it 2 more times. So one more time, and then these 2 H2s with 1 more O2 here, gone, in place 2 water molecules. And so you see at this point here, these 2 O2s are left over with no H2s to pair up with. So on a particle level, you can picture it, you can lasso things out, you can sort of picture it more easily. We can still think about the math. We can still think about how for the 7 we needed 14 H2 molecules. For the 7 O2s, we only needed 5 O2s to react with the 10 H2s. We can also do the math here. One last check of the math would be something like, let's do the number of molecules of H2O that are produced in the reaction of 10 H2s fully reacting. So 10 H2 molecules for every 2 H2s, we produce 2 waters. So we should get 10 water molecules. And then if we also think about the problem one other way, a very common way of solving like a limiting versus excess reactant problem that I know like high school uses a lot, I remember it from high school, I still remember some things from high school, is like figuring out how much product you can make off of each of the reactants. So like you can go through the problem and say, well, what if all the O2 actually reacted here? So how many molecules of water would we get if all 7 O2s were to react? Well, there it's for every 1 O2, we're getting still the 2 waters from the balanced reaction. So we're looking at our balanced reaction coefficients, and for every 1 O2 in the reaction, we produce 2 H2Os. And so this would give us 14 H2Os. And so here we'd be comparing which of the reactants produces less product. And once we get to the less product point, we've consumed that reactant. So once we get to 10 waters, we're out of H2s. So the H2s are being lost, water's being gained. So at this point here, the H2's gone. We don't have enough H2 to get to the 14 from oxygen. So one way of double checking the limiting reactant problem, or another way of doing the problem from the start with different ways information can be given to us, is to take maybe the 2 reactants, see how much product can be produced from either, and once you make the lesser amount of product, you've consumed that particular reactant, so that must be the limiting reactant. So you're looking for the less product here. So the lesser is better in this case because we've run out of H2 in that reactant. And so we'll see some problems that are probably more easily solved with the dimensional analysis process and a particle diagram process with that type of problem strategy. Okay, so in this problem here where we have 2.5 grams of H2, 25 grams of O2 react together to form water. Which reactant is the limiting reactant? Which one's the excess reactant? Now, the one thing I want us to not necessarily do is just look at H2 and say, well, it's less, it has to be H2 is the limiting. H2 could be the limiting reactant, but it's not necessarily going to be because this mass is less than this mass. It's all about the stoichiometric excess. It's all about the ratio of the moles of H2, and we just need twice as many moles of H2 as we do oxygen. And so if I'm trying to figure out which reactant is limiting versus excess, I could do this problem several different ways. I could calculate out the moles. I could think about a BCA chart. I could try to make some sort of a picture maybe of relative number of moles represented as molecules. I could do things like that. The 2 dimensional analysis steps I might try to solve if I want to do this with math would be either addressing one of 2 questions. How much of one reactant do I need to react with the other? And then maybe flipping it and calculating how much of the other reactant I need given the other. Or we could calculate how much product we can make off of each and see which one makes lesser product, and that strategy we were showing in the last example. And so if we have a 2-step problem where the next step says, well, how much of the excess reactant remains? Like if that's the second problem that we need to do, then probably the first step makes more sense to say, well, how much O2, how many grams of O2 do I need to react with all of the hydrogen? And one of 3 things is going to happen here. When I get my answer, if I figure out how many grams of O2 I need to react, I'm either going to see that it's exactly 25 grams and they're both consumed. Rarely is going to happen in these problems because they're usually intended to have one of them be in excess. I could find I need more O2 than what I have available. That would be bad because I don't have that much O2 present. Or I could find that I need less O2 to react with H2 than what's given, and then I've identified H2 as that limiting reactant. So by figuring out the mass of O2 here, I can figure out by one calculation which of these 2 reactants is a limiting versus excess reactant. So remember, it's still a gram to mole, mole to mole conversion, so we're going from grams of H2. Sometimes when you use H2 and O2, people get confused. When do you use 2.016 for the molar mass versus 1.008? Well, it's grams of H2, so 1 mole of H2 is the molar mass of the 2 hydrogens. So this is 2.016 grams. So 1 mole of H without the 2 is 1.008. So 2H is, of course, 2.016 grams. And so that's grams of hydrogen into moles of hydrogen from our coefficients in the reaction, which we previously used, but we should probably make sure that we're picturing the balanced reaction of 2H2 plus O2 goes to 2 waters, so that we get our right coefficient here, that for every 2 moles of H2 that reacts, I need 1 mole of O2 to react with it. So this is what I'm getting from my coefficients in the reaction. And that's why, of course, the reaction has to be balanced, otherwise I'm screwing up the math at this step. And then the last step would be 1 mole of O2. Since I want to compare it to the 25 grams of oxygen that we have present for O2, I want to convert moles of O2 to oxygens, 32.00 grams. And so I calculate that I need 19.8 grams of O2 to react with this quantity of 2.5 grams of hydrogen. Now, which reactant's limiting? Which one's in excess? Talk with your neighbor for a second. Just make sure that you guys can agree with me before I tell you. Because it seems pretty obvious, but I want to make sure you see it's obvious. Okay, so does everybody, well, that's a weird way to ask it. Does anybody think O2 is the excess reactant? So I don't think any, yes, O2 is the excess reactant. I said it wrong. So yeah, so O2 is the excess reactant. Did anybody think O2 was the limiting reactant? That was the way I wanted to ask it, because I don't think anybody probably does from the conversation, because it's just really being in tune with what the question's asking. It's making sure we're clear that the 19.8 grams of oxygen is the mass that has to react with the 2.5 grams, such that this mass is now down to 0, and that this mass is now down to 0. So 19.8 grams is gone. This mass of H2 and O2 are now in the form of water. And so the amount of oxygen that remains is the amount that was initially present minus the 19.8 grams that was initially present. So how much of the excess reactant remains? 5.2 grams of O2 remains. Because we needed 19.8 grams to react. We had 25, so we have that excess of 5.2 grams. Now, to be fair, I didn't remember which one was limiting versus excess in this problem. I didn't remember if it was H2 or O2, so I just kind of got lucky. If we had gotten unlucky and we started with the O2 converting into how much mass at H2 we need, I don't want to run through the math on that one, but I think you can imagine, as long as we didn't make a math error, we're going to need more H2 than we had available. And so we would have ended up with probably needing like 3 grams of H2, but we only had 2.5 grams. But you see, numbers are always subtractable, so you could always take that mass minus 2.5 grams and think that's the excess of H2, but that's not right. We just have to be in tune with, this is the mass reacting, this is the mass of O2 that reacts with it, and so that 19.8 grams is gone, so we're taking the initial O2, subtracting the 19.8. I imagine a few of you might be uneasy still with the 5.2 grams. I'm just like not being quite sure on why. Like maybe you understand 25 minus 19.8 is 5.2, but you're still not quite sure why we did the math that way or why that works or how you're going to remember that. The BCA chart might be useful here. If I use a BCA chart, it's going to have some minuses in it that's going to help us understand the difference between the change of the reaction of what's being reacted versus what remains after. And so if I'm doing the BCA chart, you can write the masses in here, just don't write that on the B line. Write the B line in where you convert those to moles. And so I just converted H2 dividing by 2.016 and then O2's dividing by 32.00 to go to their number of moles. Now, once you have the mole ratios, do you kind of see how we would need twice as many moles of O2 in the form of H2? So we need like 1.5 plus moles of H2 and we don't have that quantity. Once you write the moles out, you can kind of see the limiting versus excess reactant just by thinking of that 1:2 ratio. So you can kind of work out the limiting reactant problem if you have the moles written out like this without even solving the problem that we had just gone through. If you think about your change, the minus 2x, just a 2 in front of x because of the 2 in front of H2, minus x in front of oxygen, and then minus plus 2x for water. Now, if you know H2 is limiting, then you know this goes to 0. So if we know H2 is limiting, and I think there's two ways we can know that, one from the problem we did earlier, and the second one from the ratio of the moles. But we could be still not sure. Depending on some ways, the coefficients could be harder to interpret than these, and so maybe we don't know for sure. So you can always test this by solving for x. So x would be equal to 1.24 divided by 2. So 0.62. And then we're going to lose 0.62 moles off of oxygen, minus x. And so the amount of oxygen that's remaining in number of moles is going to be the 0.781 minus 0.62. And so if we ever were to get a negative number here, then obviously we did our limiting reactant, we chose our limiting reactant incorrectly. So if we were to ever do this math, get our x, plug x in here to work out the other reactant, if we ever get that it's negative, you can't have a negative amount. If you get a negative amount, then we chose the limiting reactant wrong. So you can use this approach to find a limiting reactant if you don't need it, or catch a mistake if you made a mistake in your identification. But you can see here that we're getting see how we get the difference between the 0.61, or excuse me, the 0.62 is the moles of oxygen that reacts, versus the difference of 0.781 and 0.62 of the oxygen that remains. So 0.161 moles of oxygen remains present in excess, and then 32 grams per mole is 5.2 grams. And so if you weren't sure why we were doing 25 minus 19.8, we can convert to moles, figure out x, get our massive moles of O2 that are remaining, convert to moles. And so, and just to show that one step here, we're just doing 1 mole of O2, 32.00 grams. That's how we arrive at the 5.2. So stoichiometry is kind of like the silly ways that we teach math these days that aren't so silly. I'll get your question in 1 second. So it's kind of like the process of learning how to count big numbers. There's like 50 million ways to do it. They all work. You just choose the one that's best. Like you could go to a calculator, do dimensional analysis, but you have to understand the steps before those work. You have to understand a chart, a picture, and those sort of things to hopefully make sense of that. Yes? So I get the 0.161 by, if you're in tune with there being 0.781 moles of O2 present, and then once I figure out x, then I know that we're taking, so I solve for x. I solve for x here is 0.62, and then I plug that x in here, and then I take the difference. And so I don't think that's also the most intuitive thing in the world, but just remember that the BCA chart is just telling you for every 2x of hydrogen you lose, you're losing half as much, just x, off of O2. So the key of the BCA chart is you get the relative ratios of the elements that are being lost versus gained. Like without even solving for water here, you can see that water is 1.24 moles, because that's 2x. So we're making 1.24 moles of water times 18.02 grams. So if we were asked the mass of water we're making, we get that from the chart too. Now, one last thing I'll say on this example before I move on is when we looked at the first problem here, we could always apply a lesser, a longer problem-solving approach if it still gets the answer. Because I mentioned before, most of you guys are probably in tune with figuring out how much water you make off of each reactant. Take all of the H2 to water, take all the O2 to water, whichever one makes the less amount of water is the limiting reactant. So I may look at that step and say, well, that's going to take us more time because then we're going to have to do that math twice, so do two-dimensional analysis steps, and then we're going to have to go back through and figure out how much of O2 reacts with the H2, do that problem, then do the subtraction step. Even though that's more steps, if it gets us the answer and that's the way we know how to do it, then let's do that. So there's always going to be the fastest way to solve a problem. There's always going to be the sort of most particle representative way, the most diagram heavy way to represent the problem. And there's always going to be some other math steps we can do that can help us get to the answer and understand it. Okay, so let's look at a problem here. One thing I would recommend, whenever you see a problem you think is one problem, we have to read carefully and make sure it's not a different problem. So be careful when you look at dimensional analysis problems to carefully read the information. We can't just start looking at the masses and running, because some problems may give us some peculiar or different information. Let's read through this problem together. So here we have 12 grams of hydrogen reacting with an unknown amount of O2. So we're told 76 grams of water forms by the reaction, how much H2 remains, and how much O2 had reacted. Okay, and they're giving us the reaction, same reaction as before. Well, what I want you to brainstorm for a second, and maybe just thinking of it, we'll maybe have a 30-second pause, of just which step do you think you want to use to solve the problem? The three steps I might think are just converting to moles and kind of picturing the moles and trying to think about that. 2 might be dimensional analysis, and then 3 might be like a BCA chart. How many of you guys are thinking dimensional analysis? I'm just going to plug and chug some numbers and work it out. That's fine. That's probably the way I would go about the problem. How many guys would make a BCA chart? A couple hands go up. A BCA chart to me here does make a lot of sense, like as a tool to solve this problem, because they're kind of telling me something that's present before. I'm getting some information about before, and I'm getting, this is like an unknown, this is obviously 0, and they're telling me how much product I'm getting after. So they're telling me like what I'm getting after, so I can work like the 2x here out pretty easily for H2 and O2. Like, I can probably set up a BCA chart here. And the reason why I might do this would be, they're telling me how much I get after. Do you see how from knowing how much you get after, you can right away solve for x? And then x can be plugged in, and as long as you convert things to moles, then the BCA chart could work just fine. I might show the BCA chart approach after we go through the dimensional analysis step. But I think if you have some thought on how you might set up a BCA chart, and you go, oh, but I can just do dimensional analysis and that'll be faster, then I think that's good thinking. The way I might solve this problem here is to, and I don't know which step you guys might think to do, but I might think to say how many grams of H2 are required to react to produce the 76.0 grams of water. So in order to get this, how much of this do I need to react to produce it? Might be the first dimensional analysis question that I try to solve. So I just use the molar mass of water, 18.02 grams per mole. For every 2 moles of water that are produced, we need 2 moles of H2 to react with it. So 1 mole of H2, whoops, wrong spot. So 1 mole of H2 in the denominator, the molar mass, 2.016 grams. And so I initially had 12 grams. So before I had 12 grams, and then I consume 8.50. So that leaves me 3.5 grams. Perhaps 3.49, maybe I rounded something wrong, but 3.49 grams of oxygen remains. Now, how much O2 reacted? Now, interestingly enough, this seems to be the answer, just because there's no other choice at 3.49 grams. But if you want to calculate the mass of oxygen that reacted to produce this quantity, that would just be doing this problem again. We can just start with the 76 grams of water. One mole of water, or excuse me, 2 moles of water when it's produced needs 1 mole of O2 to react to produce it from the coefficients in the reaction. And 1 mole of water, or excuse me, 1 mole of O2 is 32 grams. And so that's 67.5 grams. So if I go back to the BCA chart for a second to kind of show how I might use it to solve the problem, I'm just probably writing moles in because, again, that's the reacting unit. So I might be writing 4.22 moles of water in here. You don't necessarily have to do this once you know the answer, but an alternate approach might have been, well, let's just convert the 76 grams of water into moles, and right off the bat, you see that X is equal to 2.11 moles. And so then you know that you're losing twice as much of that moles, 4.22 moles of hydrogen, can convert that to a mass, and then you can convert how much oxygen, moles, X, so you just be taking that times 32. So this divided by 2 times 32 would give us that 67.5 right off the bat. So BCA chart, not a bad approach. Actually, it might even be a quicker way than the dimensional analysis approach, but it's all about making sense of the different pathways that we can use to solve these problems. Okay, so the theoretical yield, I know bio has a test this morning, so a few people have that bio exam. Who has Friday exams? At least we have Wednesday night exams, like that's better. Theoretical yield. So theoretical yield is the maximum amount of product that can be made. It's the amount of product that's possible calculated through the stoichiometry of the problem. So if you use the stoichiometry, that's how you predict the maximum yield of your reaction. That's your theoretical yield. And then, of course, you can get whatever actual yield you can imagine. So the yield doesn't have to be 100%. Generally, the yield specifically of a product can't exceed 100%. Like you can have impurities present, like maybe you're producing some compound that should only have a yield of 100 grams, you get 110 grams. Maybe there's a little bit of residual water. So maybe the sample's still wet or something. So you can have other substances present, but the actual yield of your product itself as that compound can't exceed 100%. And so our maximum yield 100%. And so our percent yield, of course, is just our actual yield divided by the theoretical yield times 100%. So however much you actually get times the theoretical yield. Let me just look at this. Yeah, so that's on this slide here. So our percent yield is just actual divided by the theoretical yield. Sometimes you can think of this as just your maximum yield. And so let's just look at this problem real quick and just take a quick notice of it, and we'll come back on Monday and just start working through this particular example. But it's just giving us some different quantities, and we can balance the reaction, and then we're only going to get some lesser quantity of moles so we can work out a percent yield from this. So our percent yields is just working through the stoichiometry to get our maximum yield, still thinking about a limiting versus excess reactant problem usually, so we still have to solve which reactant is limiting versus excess, and then we solve the step there to get our percent yield. And then we'll take from this notes just one more particle diagram question. I'll have a second set of notes of some study problems that we'll work out in class. I'll put that up over the weekend. We'll work on that in class Monday and Wednesday next week. All right, guys, that's all for today. Have a great Friday. Take care. Bye.